Hello and welcome to my presentation on the magnetism of first-row transition metal complexes. Now, paramagnetism, you can see here, occurs due to unpaired electrons within a transition metal complex. Now, each electron within the complex will have a magnetic moment. One component would be associated with the spin angular momentum, and the other would be associated with the orbital angular momentum. Now, for many first-row transition metal complexes, the second component can be ignored, and as such the magnetic moment will then be regarded as the number of unpaired electrons, or in each case can be regarded using the spin only. Now, spin only formula here for the octahedral transition metal complexes are high spin d5 and low spin d5. So here is calculated. Now, there are 5 unpaired electrons within the high spin d5, and as such, using the calculations, we'll have 5.92 Bohr magnetons. Now, in the low spin d5, where there's only 1 unpaired electron, we'll only have 1.73 Bohr magnetons for the magnetic moment. Now, in a tetrahedral d6, yet again there are 4 unpaired electrons, obviously high spin. There's going to be 4.9 Bohr magnetons for the magnetic moment. Spin-only formula, the predicted magnetic moment correlates fairly well with the measured mu effective of the transitional metal ions. Spin-only formula, the predicted magnetic moment correlates fairly well with the measured mu effective of the transitional metal ions from the first row of the D block. As you can see here, the predicted spin-only of our transitional metal complexes matches fairly well across here until roughly D6 and D7, to where the measured and observed magnetic moments of our complexes are significantly larger. Now, a reason for this variation, as well as D8, this variation is likely due to other external factors, such as the angular momentum. Now, this is the measure of the complex would then be larger than the calculated spin only. Now, this is due to the magnetic moment arising from both the spin and orbit angular momentum. Now, in order for an electron to possess orbital angular momentum, it must have, firstly, the possibility of rotating the orbit it occupies into an equivalent and degenerate orbital. And also, there needs to be space free in the degenerate orbital for an electron with the same spin to move into. Now, in high spin octahedral complexes, D1, D2, D6, and D7, all of which are high spin, will have the most notable effect. And in tetrahedral complexes, D3, D4, D6, and D7 will also have the most notable effect. Now, this orbital angular momentum can only occur in the T2G orbitals. Now, this is due to the T2G orbitals, which are dxy, dxz, and dyz, having equivalent and degenerate orbitals with one another. Obviously, in the EG, this is not the case, to where electron cannot move from the dz squared into the dx squared minus y squared. Now, in many first-row metal ions, the spin and orbital angular momentum of the electrons are independent of one another, and as such, the Van Vleck formula can be derived. Now, using this equation, we can calculate the effective magnetic moment using both the spin and orbital angular momentum. However, this equation strictly applies to free ions. In a complex, the crystal field will quench the orbital angular momentum. If there is no contribution from any orbital angular momentum, then the above formula will simply reduce down to the spin-only formula, as mentioned previously. Another factor which could increase or decrease the calculated spin-only magnetic moment will be spin-orbit coupling. Now, spin-orbit coupling is a constant, can be obtained from the total angular momentum quantum number J from the quantum numbers L and S. In a D2 electron configuration, the terms arising from the microstates is 3F, which is triply, which is a triplet F term. We have a singlet G term, singlet D term, a triplet P term, and a singlet S term. Now in the triplet F and P terms, there will be 3 J values, or 3 J terms. Whereas in the singlet terms, there is only one possible J term. And the J term is related to L plus 1 to L minus 1. Now the energy difference between J and J plus 1 states is given as J plus 1 lambda. Now lambda is the spin-orbit coupling constant. The energy difference, for example, between 3f3 and 3f4 pair is 4 lambda. In a magnetic field, each state with a different J value will then split again to give 2J plus 1 energy levels separated by what's known as the Landé splitting factor and the magnetic field. Multiply that with the Bohr magneton. Due to spin-orbit coupling, a mixing of terms will occur. The 3A2G ground term of an octahedral Da ion mixed with a higher energy 3T2G term. As you can see here, the effective magnetic moment of your complex will be calculated using your spin only, multiplied by 1 minus your alpha, which would be 4 for an A ground term and 2 for an E ground term, multiplied by your spin-orbit coupling constant, divided by your delta oct. Now, this can also be calculated in a tetrahedral complex using delta tet instead of delta oct. Here's a table, as you can see, of the spin-orbit coupling constants for some first-row transition metal ions. Now, for transition metal ions with a spin-orbit coupling constant that is positive, the calculated magnetic moment will be lower than the spin-only magnetic moment. And the inverse can be applied to those with a negative spin-orbit coupling constant. For example, the effective magnetic moment of D6, D7, D8, and D9 ions, which would be your Fe2+, cobalt, nickel, and copper 2+ ions, will be greater than your calculated spin only. Finally, we come to types of magnetism. As you can see here, we have paramagnetic, ferromagnetic, and antiferromagnetic. Now, ferromagnetic, which are aligned dipoles in one direction, and they are quite closely related, well, very closely related. And we have antiferromagnetic, which are oppositely aligned dipoles that are also closely related. Now, as you can see here, as the temperature increases for an antiferromagnetic species or complex, it becomes more magnetic. This is due to having more energy in the system. These close particles become less closely related and more separated, and therefore the oppositely aligned dipoles will be weaker and become more magnetic. Now the opposite will be applied to a ferromagnetic species, to where the aligned dipoles become weaker, the particles are less closely related, until they both reach a point, the Curie point for the ferromagnetic species and the Neal point for the antiferromagnetic species, to where they will end act as a paramagnetic species or complex.